All right, hey guys, this is Owen Nix here again. Just kind of keeping this discussion about the phenomenon going, and I just wanted to kind of reiterate some things I touched on in the very first webinar, and kind of expand on a couple other things that I've done and experienced, and that I think you could do too, just based on the fact that our phenomenon really doesn't necessarily have to be this great production, this big wow type event, because a lot of times those may be cool and kids may want to take a picture of that in the classroom or put it on social media, but sometimes they don't actually get the science part out of it. And that's why a lot of times we try to find those ways they can do things for themselves and kind of ways they can do the science. So how phenomena were introduced to me, and not to say that I wasn't aware of the phenomenon aspect of science. I think that's why we're all into teaching science. But I went to a science ambassador training, and we were asked, just kind of from the top, we were introduced to these people we didn't really know yet, and then we were asked to go outside and collect some different kinds of leaves. And that was pretty much all we were asked to do. We didn't know why we were collecting them. They didn't tell us. They gave us like a number to collect, I think. And we were just told to collect leaves and come back. And so you had people who collected anything from blades of grass to something, on a piece of pine straw. So any kind of leaf we collected and brought in. And what we were asked to do when we got to our table is we looked at and we classified these leaves, and we just in different ways. They didn't tell us how they want us to do it, but naturally, the color classification came out, shape, texture, stuff like that. So that's kind of where we started. And then we had some discussion about that and the different ways we classified our leaves at our different tables. And then eventually the instructors narrowed that down, kind of narrowed the focus of that to color, and more specifically, why leaves are two different colors on the top and bottom in most cases. The ones that have a top and bottom, something like a needle might be a little different, but it still has the same general functions. So from that, our next steps were to investigate why they were different. For me, I'm not really a bio person. I haven't taught a lot of bio, and the last time I had it was in college several years ago. And so, to be honest, I'm sure we went over this at some point in my high school or college career, but it's not something I remembered. So to me, it really put me in the role of a student, because I was kind of interested in why they were these different colors. And I knew it probably had something to do with the roles, but did I know exactly what the roles, or really what the bottom of the leaf did? Because, I think everybody remembers photosynthesis, and we don't really focus on the bottom of the leaf that much. So that whole introduction to this phenomenon really did get me interested in something that I wasn't very familiar with. And I think that's what we're trying to do with kids. A lot of times there's some structure there of what we want or where we want them to go, but then it's just kind of getting them to that point. So what we did after we found out and researched why they were different is we were asked to create a poster highlighting some data. We were asked to potentially draw what's going on, or maybe some people just chose to draw, and I'm thinking that's what we were asked to do. And then basically just shared what we wanted to about the topic and what we learned, and everybody had a little bit, something different to say. Now, it was a big room with a lot of people, so eventually, after the first few people presented, we did get a lot of the facts out. But in a classroom setting, you're probably going to get something new from each group. Now, this was great in person, but now it's kind of how does that translate to the virtual aspect? And I'm really try to speak on that a little bit more in the next session about some different ways to get that collaboration and presentation type feel from our virtual setting, or even in a setting in a classroom where we're not really allowed to interact physically with the students as much, or maybe students have restrictions on how far they can sit away and not working in groups and stuff like that. So really, we've got to figure out some ways to still allow that collaboration to happen. So I'm going to speak on that in the next one. But today, I'm going to go back and focus a little bit more on ICE in just a minute. So as someone who's not been in bio, since I said earlier, I wasn't really just curious about the leaves. I was also curious about the role of the bottom side, just because I didn't remember that. And I think that's where students are, because they, they're not experts on the topics that they're learning, but a lot of times they know a little bit about them because they've either experienced them in real life, especially in the physical sciences, or they learned a little bit about it in this grade or that grade, and there's a little bit of knowledge there they can draw on. So I think, our role is to remember that there is probably some basic understanding of the concept there, but that we are really the experts. So that space between, we have to come down a little bit to get to them, but they also are capable of coming up a little bit to get to us. So with the physical science phenomenon, when we were introduced to this topic, we were given ice cubes, and these cubes were just like, regular size ice cubes, out of a bag of ice you buy at a convenience store. And then we were given multiple surfaces, and these multiple surfaces range, in types of the surface from metals to like a paper towel. And all we were asked to do is investigate how the ice behaved on the different surfaces. So this is kind of just the physical science example after we kind of worked through the bio example in the beginning of the day. So after the investigation, we were asked to draw conclusions about the results. They didn't tell us what they wanted us to, how they wanted us to collect data. They just basically wanted us to make observations of what was happening. And I think a lot of times that's all we're doing. We're asking students to make observations, to get the wheels turning, and then when they start presenting those conclusions, we help them clean them up if they need help. A lot of times they're on the right track on their own. So the materials we had in our setup, we had ice cubes. We tried to get similar sizes, of course. We had these metal squares covered in tinfoil. We had napkins. We had a piece of tile. I think we just set one on the table too. There may have been some other surfaces as well. And we recorded the actual time, but you really just needed to observe what melted first. So back to the why of the phenomenon, right? So we're there to get the wheels turning. We want them to start to question what's happening, or maybe their understanding of what's happening. And then we want to get them to that wonder piece. And we do that by figuring out what they do know and where they are at, and then we help connect them to where they want to be. So it's important to remember, like I said in the opening, that it doesn't have to be phenomenal. It can be something that just allows the student to get involved in the thinking process, and to where they're not just being told what's going on in a demo or something like that. Now, demos are great, and they're wonderful to help students understand what's happening, but a lot of times we do a demo after we've given them the instruction, or sometimes we do a demo and it's so early on in the process that they can't even think about what's happening. So with a demo, it's really nice to have something that they can tangibly do that helps kind of drive that point home. So videos are great as well, and we have to use a lot of those in the virtual setting, but it's also nice when we can get a video that maybe gives us one perspective of what's going on, maybe on a scale that we can't provide students at home or in the classroom, but also accompany it with something that they can actually do and see what's happening. So my first segment, I did one on gas laws, and I compared what they could do with their fridge and their bags that they had, or gloves or whatever. And then I showed them a video in that of what happens when you pour liquid nitrogen on a balloon, which obviously they don't have access to. But that kind of helped them connect the two, and it also provided something for the students who truly had no materials to do what they needed to do, an ability to make some observations. So kind of something I have thought about as I went through this process is we have to get the bulb into the socket before it can actually light up. I think a lot of teachers talk about the bulb and the light bulb going off and seeing that, but I think it's important to remember that light bulb doesn't just show up out of nowhere. A lot of times we have to help get it into a position to where it can glow and it can shine. So in thinking about what we're doing, we have to think about the materials they have at home. So when I started getting virtual students, and that's even going to change with me coming into the next half of the year, which I'm sure a lot of you guys are having changes in your schools the next half of the year too, with either more students going virtual or some students coming back or having some hybrid stuff. But I had to sit down and think about what students had at home. I know what I have in my home, but what are students going to have at their home? So first I looked through my things and kind of said, okay, what are some things that I could use in a science classroom, or that I do use in my real science classroom, that I also have at home without, without students have to go out and buy, or students can't participate, they don't have. So I just came up with a list of some things that I thought about. Plastic bags, most of them have access to a fridge or microwave, ice cubes, paper, those kind of things, paper towels, and obviously there was lots of other things there. But we have to kind of start thinking about what's available to them at home. So that's kind of our limitation, is what they have access to. And then where we can expand on that and go above that limitation is if we, find a video or something like that that can help supplement what we're doing, or what they're physically able to do in their rooms, or excuse me, at their homes. So looking at that, we have to ask what they can do in class that can be done with materials at home. So a lot of times we do stuff in class that's relatively inexpensive because we're maybe providing our own materials and things like that. So a lot of the materials are things that come from what would be their home. And so we have to start there. Also looking at labs or even virtual labs that we've kind of developed, and figuring out where could I take a piece of that and actually have them do it. So like going back to the gas laws example, I did some virtual gas law stuff with like FET for them to investigate some different things. And so then I just kind of took that virtual lab they were doing, and before they did it, pulled out a piece, which is the piece I ended up using or presenting last time, just to get their thoughts going on the process before they go and do it in a virtual setting, which, virtual labs are great, and especially for this, we're really lucky to have resources like that, especially ones that are free or available to everyone. But a lot of times students just don't get the same understanding in that virtual lab. So it's nice to have a little piece of it that's tangible that they can kind of experience on their own and start to think about before they get into that virtual lab setting where it's kind of just plug and play and make observations in that way. And then also just what can we do to get them away from their screen for a minute, or even if they're in the classroom, out of their seat. A lot of these type things could be done individually as students. I know, a lot of people have restrictions on labs and groups and all that kind of stuff. But a lot of this stuff we are looking at in a virtual setting is stuff they could do in person as well, kind of by themselves, if they didn't have the group option available. So what standards does it apply to, right? So ICE could really be used for several standards in chemistry and physical science. And even outside of that, one of the things I want to talk about toward the end, just with, they're going to microwave an ice cube, it's a pretty basic concept, but it also deals with waves. So it also ties in other standards as well, or physics standards as well. So it's not really just even going through this and creating this, I wrote these standards down, but then as I went through it, it's really not even limited to these standards either. There's some more out there that can apply from a different perspective with the microwave aspect. So back to our ice cube and surface phenomenon. So students should find that ice melts pretty quickly on the metal surface versus the counter or plate or wood or whatever else they're using, right? Because they may not have the things presented to them that we did, but most of them have a metal pan at their house or a piece of tin foil. They mostly have a counter or some sort of cutting board, something like that. And then most of them have a napkin or a towel. So those could be like the three things you suggest they use in their setting. And you want to, I would say, you know, a minimum of 3 would be good. Just to have something where you're not just relating 2 surfaces, and then they can kind of think about how those surfaces transfer energy, which is really what we're looking at. So the main standard for this one, and it kind of hits each substandard. I wasn't going to put all the substandards on there, but really, if you look at the ice cube melting faster on the metal, slower on the napkin kind of thing, it really hits each one of these substandards as well to some extent. Now, obviously some more than others, but it really relates to all. So you could even use this to introduce your entire unit that's based on standard 7, or you could use it to introduce, you know, one piece of this if you have something else you're doing for the others. It's really up to you. So how does the phenomenon connect? Well, this phenomenon can be related to the standard, like I said, as broad or as narrow as you want it to be. It can be as broad as covering each part of it, covering your entire unit, or as narrow as a day's lesson, something you speak about, you know, in part of a lesson, or even as just a warm-up to refer back to as you move throughout the unit. The last part, if you wanted to kind of expand on it and make it into a project, you could always take it and have the students create a like traditional lab from it, where they're guiding maybe other students in a little more structured way through what they did, or redesigning what they did to better understand what is going on and what you're trying to get from the phenomenon that they've experienced. So I think, you know, again, there's a wide range of things you can do with it, and obviously it's not limited to these few ideas. And that's the case with most of the phenomena we look at and things we use. So again, really good to use videos or live demos that can help expand their investigation past that point. You could have them, you know, suggest other materials that may produce some of the same type results. You know, I would remind you to not limit yourself to just the standard you're on. It's okay if it applies to others. Maybe they don't have a good understanding of that one yet, but that's okay, because you're, again, just kind of planting that seed and realizing or helping them to connect all those pieces, which is really why they're, you know, why they're all working together to get to that one overall goal, even if it pulls in some other standards that you may not be focusing on in that list. So just some other ideas on how it can be used. Students can begin to form their thoughts as to why energy or how the relation of the flow of energy and the role of conductors and insulators. Students could suggest other surfaces and maybe where they would fall in the current data set. So maybe they recorded time on the 3 surfaces that they had, which does take a while for the ice cube on the napkin. It will take them a while to get that numerical data, but they could suggest where they might fit based on what they know about those materials. So they could kind of use what they know to extrapolate some data there and put things in an order, or, you know, you could give them different surfaces and they could suggest where they would be placed. They could also collect numerical data and present that on a poster or some sort of picture chart or something like that as a group. And I'm going to kind of get into some methods or some resources that are out there for doing stuff like that in a virtual setting. And then students could also share thoughts in real time, like on the feedback platform. I've mentioned I used Pear Deck before. There's definitely a lot of other good ones out there. And even like I know Google and Teams and all this stuff have been modifying some of the things that they do to incorporate some of that in just your usual Meet or team platform that you may already use to meet with your students or whatever other ones you're on. So another simple example I just kind of thought about, again, thinking about things that kids have the ability to do at home, is a question like, how does a microwave heat up food? Now, yes, we're talking about microwaves, and yes, that has to do with waves, and that's not the standard we may be focusing on because we really may be looking more at like what are the particles doing, things like that. But it's also something that ties in, and we can always go back to and refer to when we get into waves and start talking about the transfer of energy and particle wave duality and stuff like that, and even into physics, which may not have some of the same particle motion standards that we have in our physical science or chemistry piece. But anyway, so students are just going to put an ice cube in a clear bowl. It doesn't have to be clear because they can just make observations after. And they don't need to microwave it for very long. To get the ice cube to completely melt actually does take a while and get to a point where the water's heating up into the vapor, but it's a tiny amount of water, and it's really, they don't need to get to that point. They kind of understand the concept before they even get to it. But they may think that something kind of different is going on with an ice cube in a microwave, so they probably are going to be interested to do it because most people have never put an ice cube in a microwave because there's really not a reason other than science to do it. So once they see the ice cube melting, they can stop. So usually it takes a couple minutes. Obviously, it's going to start melting right away, but really making an observation about the fact that it's melting and there's water pooling around it. It's going to take a few minutes. And then we're going to ask them just to provide observations about what is happening to the ice cube. It'll probably take longer to melt than they thought. I mean, I think a lot of them would think it would be like when you put it in a pan and just immediately starts melting and then eventually boiling pretty quickly. And it's not the case with a microwave if they're using, you know, a decent sized ice cube. If they're using like the crushed ice, it'll go pretty quick. So how to have students draw what they think is happening to the molecules in the ice. We can have them find images to help explain what they think is happening and use maybe like an infographic or something called PictoChart, which I'm going to talk a little bit about next time. It's free for them to create like 5 or so of them, which I just kind of use them throughout the year and it works out well if they haven't used them in another class. But anyway, I'll go into that next time. And then in your lesson, this can also just be related to the motion of particles, transfer of energy, and of course waves, which isn't always taught at the same time. So again, you can draw back on this, or maybe you used another standards to teach motion of particle or another phenomenon to do motion of particles and stuff like that. And when you get to waves, you can talk about this instead. So it's important to remember that your phenomena are not based on, you know, or don't have to stick with one unit. They can apply to multiple. You can refer back to them because students are going to typically remember them because it's something they did. So I know this was probably a little quicker than last time we got together. I hope next time to get with you guys on some of these resources and things you can use to help collaborate amongst your students. I know there's a lot of different things out there and every platform has something different. I am most familiar with the Google stuff, but I have been learning a little bit more about Teams because I'm using that for some other things. And then I also have access to some Zoom stuff. So I will be looking through a lot of those things. If you have suggestions for something you're doing in your room that, or in your virtual classroom, and you're just not, you haven't found a good system or a good way or a good resource to use for doing that, please reach out and let me know. you can send me an email there at my school email, or you're welcome to use the platform that we have set up as a part of this kind of physical science teachers group. So I look forward to hearing from you guys, and I will see you next time, probably in January. So have a great break and a much deserved bit of rest here before we tackle this second half of the year. Good to talk to you guys again. Have a good one.